fields in the last message to reduce the number of probes. So that's the basic idea on how we solve these two challenges. In ShieldGen, we do the probe generation in in 3 steps. First, we handle buffer overruns because it's a common attack. Second, we remove irrelevant iterative records. And third, we do a sampling on the data fields. So key condition, we want to handle buffer overrun first is because buffer overrun is very common. Second is there's a key condition for buffer overrun is to check the vulnerable buffer size. And how to tell? First, we need to solve the problem is how do we tell it's a buffer overrun? We leverage a heuristic. It's basically saying if the offending byte returned by vigilante sits in the middle of a string, then sits in the middle of buffer or byte array, then that's a buffer overrun. Once we find the buffer overrun, we will add a condition in our vulnerability predicate saying the buffer size must be larger than the offset of the offending byte in the string. This tells us the minimal size the buffer overrun attack must have. And secondly is we handle the record sequences. Many popular input formats have iterative records, like the example I showed earlier, like HTML header or this media files. It's a sequence of frames. And the problem is typically only one iterative record in the attack instance matters to the vulnerability. It's only one record. For example, in a WMF attack, it's only one record that will trigger the attack, exploit the vulnerability. All other records doesn't matter. So the problem is if we don't remove iterative records, those irrelevant records, any conditions on these irrelevant records will cause false negatives because those are too specific and not unnecessary conditions.
Hello, how are you?
Our advantage here is we can handle iterations because they are specified in the spec, either specified in GAPA spec or they can be inferred by Tupni. So we can handle these record sequences. I will use a simple example to explain the basic idea of how we remove irrelevant records. Assuming we have a file input, and the semantic, we parse this file. Say the file has a header and a body. The header has a type, specify the file type and the size, and the body is a iterative record. It's a record sequence, and we parse the body to 3 records, and we continue that we parse each record. And assume that vigilante, the 0-day attack detector, tells us the offending byte is in the second record. Then we'll mark the second record as this offending record. And the first thing we do is we remove all other records in the input. Here, I want to point one thing is we fix the size because the size specifies the file size. After we remove these records, the file size must be adjusted so that we get a valid input. Then we feed this file into the vulnerable program and see if the vulnerable program will be exploited. The 0-day detector, if the vigilante tells us saying, oh, this new file doesn't trigger alarm, then what we do is we add the records back and we remove one record and see if it will still trigger the attack. If it still doesn't, we remove another one, see if it will work. Of course, this is just a basic idea, is see how we can remove irrelevant records. In our actual implementation, we remove the records exponentially so that we don't need to enumerate all the combinations. And the last step in probe generation is to sampling data fields. The goal here is to relax the conditions on the fields left after we remove the irrelevant records. The problem is combinatorial exhaustive search is not followable because even a 4-byte field, there are 2 to the 32 possible values. And our target is we want to derive the simple vulnerability conditions. In other words, we want to find a conjunction of conditions on individual fields. We don't look for the combination of on 2 fields, the conditions on 2 fields. And our approach here is to sample data fields independently to find the don't care fields. The don't care fields is basically saying this field can take any arbitrary value. It doesn't matter. It doesn't matter to the vulnerability. And theoretically, I want to point out is sampling may lead to both false positives and false negatives. For instance, if we miss possible values of for attack, then we'll have false negatives. Uh, Also, if we're mistaking a field saying it's don't care because we only sample certain values, then we'll have false positives. We'll miss some attack. But in our evaluation, we found that we didn't observe any false positives by doing some sampling. So ShieldGen is we implement a prototype of ShieldGen based on Vigilante, GAPA, and we implement a standalone component to do the probe generation and the vulnerability predicate derivation. And we evaluated ShieldGen based on three metrics. First is accuracy and efficiency and coverage. We we do it in two ways. First, we do a case study. We analyze vulnerabilities behind the Slammer, Blaster, and WMF attack. And secondly, we did a vulnerability coverage study to see how many vulnerabilities can be analyzed, or ShieldGen can derive the vulnerability signature for these vulnerabilities. So for accuracy, as I said, we didn't observe any false positives for the three vulnerabilities. And however, we have false negatives. The reason are mainly twofold. First is we may have an imprecise data spec. If the data spec is not accurate or complete, then we may have false negatives. And second one is we do a sampling. So when we do a sampling, we may have false negatives. For example, WMF have two version numbers, and it's really hard to find the second version number simply by doing sampling. Then we draw a wrong conclusion saying, oh, the version number must be 1.1. Just an example I give. Then we'll miss any WMF exploit that has a different version number. This is the constraints of limited sampling. And but compared with the previous systems, ShieldGen has a far less false negatives than previous system. For example, we can remove iterative records, irrelevant records in WMF. What we find is that you only need one record and one arbitrary record. That's only the two conditions. However, if we don't have a ShieldGen, you can construct an arbitrary WMF file that will exploit the vulnerability. You can have a 10,000 bytes file or like a 1,000 byte file. At the end, we find out you need at least our signature says you have a 112, 118 bytes that will exploit the input. And for RPC, we find out 22 fields are don't care fields, and previous solution will give a specific condition on that. And for efficiency, we only need to generate a small number of probes since we do a sampling on them. And also, for the iteration removal, we do it exponentially. And in our evaluation, we did this vulnerability coverage study. We did a pencil and paper study on 25 out of 157 data patchable vulnerabilities. Basically, in the 3-year frame, Microsoft issued 377 security bulletins, and we went through all the 377 and found that 157 out of them are data patchable, means we can have an input filter to filter the attack instances, because rest of them are either access right escalation or cross-site scripting attacks. And for the 157, we randomly pick 25, and in the 25, we found out that 19 of them ShieldGen can generate a data patch. For the six cases, 6 vulnerabilities, we cannot generate data patch. The